PocketBase is engineered around a specific architectural premise, an entire backend infrastructure, including an embedded SQLite database, compiled into a single executable Go file. In early development, that single file is easy to manage, but as an instance scales into enterprise production, the underlying state generates a significant physical footprint. This directory properties dialog reveals the scale of a mature instance, rapidly accumulating nearly 750,000 files and over 6 gigabytes of data. Every record, upload, and internal routing log is written into a single directory known as pb.data. When it comes time to upgrade the PocketBase executable, this dense local state presents a direct operational hazard. Overriding the binary requires a strategy to protect the data it relies on. Safely navigating an upgrade depends on entirely decoupling that local state from the application file. Open-source backend projects frequently undergo structural code revisions that break existing API routing syntax. PocketBase reached this point between version 0.22 and 0.23. The API was aggressively refactored, creating a hard dividing line between legacy codebases and modern deployments like version 0.39. Legacy deployments with extensive custom backend routing cannot simply download and run the newest binary over an existing environment. Attempting an in-place upgrade without a strict extraction protocol risks corrupting the PB data directory and rendering gigabytes of production state unreadable. To bypass this risk, DevOps engineers rely on a specific extraction sequence, known as the Docker swap. This technique treats the Docker container hosting the binary as ephemeral, while the local file system holding the data remains permanent. A typical PocketBase Docker container organizes its logic into 3 distinct directories: pb.data, pb.hooks, and pb.migrations. The pb.data folder houses the embedded SQLite database and all physical file uploads. The pb.hooks folder contains your custom routing logic, while pb.migrations tracks incremental changes to your database schema. Step 1 of the migration protocol involves extracting these folders out of the container and mapping them to a stable host machine volume. Once the state is isolated, delete the old Docker container, update your Docker file to target a newer version, and spin up the new environment. Before the new binary boots, map the extracted host folders back into the fresh container, re-injecting the old state. While this physical swap protects the data, you must still carefully review the changelog for internal structural updates, such as strict new limits on JSON field sizes that might reject existing records. Mastering this maneuver transforms a coupled local state backend into a modular system, where application logic can be swapped out cleanly. Data extraction solves the physical migration, but it cannot fix hard API incompatibilities in the code itself. The release of PocketBase version 0.23 completely rewrote the API syntax. For environments relying on custom routing in pb.hooks or legacy hosting platforms like PocketHost, moving to 0.23 breaks the application entirely. Developers in this position must adapt their workflow to support a locked legacy system, ensuring their code continues to function against older endpoints. This requires referencing historical documentation, which the project maintains at pocketbase.io/old, allowing engineers to bypass the modernized main docs. Enterprise architecture often requires intentionally freezing a version state to maintain complex business logic. Freezing your API at version 0.22 leads to a critical security concern. Does a locked version mean abandoning infrastructural security updates? PocketBase addresses this through a dual-track release strategy. Maintainers release critical dependency updates on the main branch, such as updating the SQLite driver to version 1.54.0. When a vulnerability is patched at the top level, that specific dependency bump is backported directly down to the legacy branch. This includes deploying security fixes to iterative releases like 0.22.51. This strategy effectively decouples the syntax of the API from the security of the core dependencies. A dual-track architecture empowers DevOps engineers to keep legacy routing logic intact without accumulating vulnerabilities in the database driver. This operational model stands in contrast to fully managed serverless databases, where version upgrades are invisible to the user. Single-file architectures provide local control and speed, but they shift the burden of upgrade safety entirely to the backend engineer. You are responsible for manually auditing changelogs for schema constraints before executing any Docker swap. Owning your state means you must own the operational discipline required to maintain it. Isolating and extracting the physical state folders is the primary defense against version corruption. When API changes threaten business logic, legacy documentation and dual-track security backports provide a viable path to stability. System upgrades remain viable for high-density local databases when the engineer enforces the boundary between the executable binary and the permanent file system.